The very last topic of this chapter involves relating delta G to equilibrium and to the cell potential. There's got to be a relationship between all three of these. Okay, so we know we kind of know this relationship a little bit because we know that we can relate delta G and cell potentials. If we have delta G at standard state, this is equal to negative N times F times E at standard state. We know that. Now, from the thermodynamics unit, we know this, that delta G at standard state is equal to negative RT natural log of K. So we know that as well. All right. Is there a way that we can relate these two equations together? And it turns out, yes, there is. If I go into this second equation and replace delta G at standard state with negative NFE, so I'm going to pop that in. So negative N times F times E standard state is equal to negative RT natural log K. All right. Now, what I want to do is solve for the cell potential at standard state. So if I divide both sides by negative NF, okay, I get this. So the negative NF cancels out on either side. On the left-hand side, the negative sign cancels out on both sides. And what I'm going to do is rewrite this expression, grouping together the RT and the N and F. So I get that the cell potential is going to be equal to RT divided by NF times the natural log of K. And there it is. So that's how this is all related. Now, we do have, just to show, just to make sure that we're all on the same page, the Nernst equation, what we've been using so far, says this. At 25 degrees Celsius, we said that the cell potential at standard state was equal to 0.0592 volts divided by the number of moles of electrons times the log of K. And so this is a special form of that equation at 25 degrees Celsius. Okay. So at 25 degrees Celsius, you can use this second equation. At any other temperature, you have to use the first equation. All right. But there it is. This is a very, very fortunate aspect of these relationships. The cell potential becomes very easy to measure, even the 5 sig figs. Okay. To find K from their concentrations can be very difficult to measure if the concentrations are very small. So the easy and accurate cell potential measurements is quite fortuitous for us. So to recap, we can calculate equilibrium 3 different ways. The first way was using concentrations, which we focused on for pretty much half of this course. Or I'm sorry, a third of this course, where it was the concentration of the products divided by the concentration of reactants. Okay. Second way was through thermodynamic data, that once we knew the Gibbs free energy at standard state, this was equal to negative RT natural log of K. Okay. Now we can relate K to electromotive force data, EMF data, that the cell potential is going to be equal to RT divided by NF times natural log of K. All right, so we can relate all of this cool stuff. All right, so what can we say about the relationship between the cell potential and K? And so here's a graph to help us figure this out. So what I'm going to do, on the y-axis, we've got K. On the x-axis, we've got the cell potential. And so what I'm going to do is drop a line at 0 volts. Okay? So I'm just going to make a horizontal line. So that kind of helps us figure out, our bearings. So there's no cell potential. That's SHE, the standard hydrogen electrode. Okay. Now, if we increase the voltage, if the cell potential increases from this point forward, what happens is that the equilibrium is going to be greater than 1. So we know that this is going to be, if the cell potential, E, is positive, that means K has to be greater than 1. So that tells us that we're going towards product formation. And while it's not being said on the graph, what we do know is that delta G should be negative, and that means it's going to be a spontaneous reaction. It's favorable. If we go the opposite direction, where K is less than 1, we know it's reactant formation. Okay. Electromotive force is going to be negative. That means that Gibbs free energy most likely is going to be positive. And so this is going to be unfavorable. And when we're truly at equilibrium, so if we go all the way to 1 and I drop a line, notice that that 1 for the equilibrium intersects this curve right at 0 volts. So when we truly are at equilibrium, there is no voltage being generated. There is no voltage being generated. Okay. All right, so we've got our final problem. Use the data in table 18.1 to calculate the equilibrium constant for this reaction. All right, so we've got some stuff going on. All right, so we got 4 moles of Fe2 plus O2 plus 4 moles of H plus yields 4 moles of Fe3 plus 2 moles of water. So there's really two reactions going on. You've got one reaction where you've got Fe2 plus yields Fe3 plus 1 electron. And the electromotive force, if we look that up on the cell potential chart, that's going to be negative 0.77. Okay, now keep in mind we've got to multiply this equation by 4, but that doesn't change the cell potential. The other equation that we've got is we've got O2 plus 4 moles of H plus 4 electrons yields 2 H2O. And the cell potential for that is going to be a plus 1.23 volts. So if we add up these two reactions together, we should get this overall reaction right over here. So that should be 4 moles of Fe2 plus O2 plus 4 moles of H plus yields 4 moles of Fe3 plus 2 moles of water. And if we add up the cell potentials, the cell potential should be 0.46 volts for this reaction. All right. So now we're told that this reaction is occurring at 25 degrees Celsius. So that allows us to use the special form of the equation where E cell at standard state is equal to 0.0592 volts divided by N times the log of K. All right. So we know what E cell is. So if I pop that in, 0.46 volts is equal to 0.0592 volts divided by N. In this case, N is going to be 4 because that's what we had for the electrons. How many moles of electrons times the log of K. All right, so what we want to do is multiply both sides by 4 and then divide by 0.0592. So that way we get log of K by itself. So log of K would be equal to 4 times 0.46 divided by 0.0592. And that would be equal to a positive 31.08. So we've got to find K. If we take 10, raise it to the log of K, that's going to give us K by itself. So if we take 10 raised to the 31.08, that gives us a K that's going to be roughly 1.20 times 10 to the 31st. So this is definitely product formation. Definitely product formation. So high, in fact, that 10 to the 31st, most likely there's going to be very little reactants in your mixture. So what can we say about the distribution between reactants and products in this reaction? We can say that the concentration of products is going to be much, much, much greater than the concentration of the reactants. Okay. And then what can we say about the relationship between Ks for redox reactions compared to acid-base reactions? They're going to be pretty high. They're going to be pretty high compared to acid-base reactions. Now, at this point, the rest of the chapter goes into applications using everything that we've talked about so far in electrochemistry. For all intents and purposes, for this summer course, this is where we're going to stop for electrochemistry. So you got the basics down. If you want to check out the rest of chapter 19, electrochemistry, and see all the different applications, that's pretty cool. Go for it. But that's where we're going to stop for this course.